Hi, these are a series of short videos that are meant to address radiant energy and its transfer and give you a different perspective from the book and to relate it to the real world. This is actually a article out of the Washington Post that is recent for 2021 about a heat dome over the US that's really causing deaths and drought in the West and in the Northwest. So we will be studying more about these heat domes and why they develop, but to get to the basics of it, you have to understand how sunshine is impacting the earth, and that calls for radiant energy and topics in thermodynamics. So let's get into it a bit more. You already know about the first law of thermodynamics, that energy cannot be created or destroyed, only transferred. And when we're talking about thermodynamics, we're talking about the energy in motion, thermodynamics. Well, let's get to the second law of thermodynamics, and that talks about the direction of that transfer. So energy can transfer, but it goes in a certain direction, and that direction is generally spontaneously from high energy to low energy. And I gave you three examples here. One example of high energy to low energy is high potential energy, that is gravitational energy, that flows from higher potential energy to lower kinetic energy, and that is a spontaneous flow when this valve is open. You would never see a spontaneous movement from low energy to high energy here. It wouldn't happen. And the second law of thermodynamics says that spontaneously a balloon which contains high energy in it, high energy molecules in it from being blown up, may leak to a smaller balloon. And that is going from high energy to low energy. You would never see the balloon blow itself up. It would never move in the opposite direction. It would have to do too much work to create that force. So this energy spontaneously moves from high energy to low energy, and in doing so, here's your third example, moving from high energy, the hot coffee moves out into the air, warming the air. So this movement of high energy or high temperature to low energy is also doing the work of warming the air in the room. Just a touch, but if you had a small box over this cup, it would warm up the air in the box quite a bit, and you would see the work more often. You don't see the energy from the air in the room warming the coffee. That doesn't happen. So the spontaneous movement is from more energy to lower energy and doing the work along the way of passing that energy through to the environment. So that's the second law of thermodynamics, and it really impacts our planet, and it impacts the amount of sunshine that we use for our energy. In fact, there is a separate sideline of the second law of thermodynamics for atmospheric sciences, the state of radiative equilibrium. And that says that all energy absorbed and creating a higher energy source on the ground will eventually emit away into the surroundings. So all energy absorbed gets emitted. That sounds like a black body, and in fact a state of radiative equilibrium is in effect in a black body, and it is in effect on Earth as well. When the rate of radiant absorption equals the rate of radiant emission, then you're in a state of radiative equilibrium. If it does not equal, if emissions do not equal absorption, you have cooling or heating. Well, let's go to the heating first because it is something that you're more familiar with. That is when emissions from a source are less than absorption into that source. So in other words, you are putting a heat lamp into your bathroom and it will emit more, your bathroom will absorb more energy than it will emit off, and it will heat the bathroom temporarily until you open the door, and then the equilibrium will start to work with the outside air. So this heating is very well known in isolated areas. In the bathroom that has the door closed, you can put on the heat lamp, and all of the towels and all of the tile and all of the sinks and the walls will absorb that radiant energy from the heat lamp. It won't emit it off as fast as it absorbs it, and it will heat that room. But once you open the door, that door opening adds the surrounding cooler air, and that air will move into the cooler air and come to an equilibrium temperature. Another example of a difference between emissions and absorptions is when the emission is greater than the absorption. When you are putting off so much energy that you are effectively cooling that environment. One place you'll see this is down at the shore during the summer on the sand at about midnight. The sand, which had been very hot during the day, has now emitted off so efficiently that it is much cooler than the surrounding air. So that's an example of a time when the sand is emitting more than it's absorbing because the sun's not out, and the sand is cooling. These are all states of radiative equilibrium. Equilibrium is so important in the biological sciences and in meteorology, which is a physical science that has some biology related to it. Now, we talked a bit about black bodies emitting everything that they absorb. And if the Earth had an atmosphere but no greenhouse gases at all, it could absorb all the energy from the sun in the atmosphere or in the ground, and it would emit just as much as it absorbed. And that would make this the Earth into a perfect black body. But you couldn't live there. And you couldn't live there because the Earth would be so cold as to not have liquid water. And liquid water is essential for life. So the Earth without greenhouse gases would be a perfect black body, but it would be a perfect black body without life, which is what we're finding on a lot of the planets that we're looking for right now. I also teach astronomy. So we're finding that there are planets out there that are close to our temperature, but they are not close enough to sustain liquid water. We will talk about what is going on with our atmosphere and our greenhouse gases in the next lab.